All right, great. If you guys remember what we did yesterday, we looked at the risers. We looked at the risers, and I showed you, I gave you a picture of the riser in this project. We have speakers that talked about switch gears, switch boards, panel boards, MCCs, and so forth. And it's very essential for us as a designers to be able to size these, how many things? 7 things for any panel that we have in our building. These are very important 7 things that you need to size for any panel that you install in your building. So Dustin, this panel could be mechanical panel, could be receptacle panel, could be lighting panel, could be owner equipment panel, any type of panel that you can imagine. These 7 things that we need to be able to size. Number 1, Chris, so let me read this one because my handwriting sucks. So example number 1, we have a lighting panel. In this case, it's called lighting panel, but it really could be any type of panel. Could be receptacle, could be mechanical. So I have a lighting panel, 48277, cool. And I calculated a load of 150 kVA. Now, Nick, this 150, remember the calculation that you guys did based on the code and the derating and blah, 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 all the stuff? You have calculated and you came up with a lump sum chunk of load 150. Can I get you guys to understand that this 150 is calculated based on the code? For example, we take 3.5 times the square foot of a commercial building, multiply it by 3.5. That will give us the kVA for the building, multiplied by 1.25 because continuous load. That's how this 150 kVA came to be. Everybody knows where 150 kVA came to be? I did calculation. You guys did the calculation for me, right? And based on this calculation, you came up with a lump sum kVA. We need to size from that kVA a lighting panel. For all practical reasons, first, this 150 kVA could be receptacle kVA, derated, completely derated, and they call it demand load. This 150 kVA could be demand load for receptacles, mechanical equipment, whatever. Can I just give me a thumbs up? We know what the 150 kVA is, demand load. We already calculated it. Cool? All right. So we know that. So when we know that, so we need a panel that can carry 150 kVA. Okay, so the first thing we need to find, guys, is a few things. Number 1, I want you to size, this one is referred to the bus inside the panel size. Number 2 refers to the overcurrent protection device that can reside inside the panel or ahead of the panel. Everybody can see that? Number 2 refers to the overcurrent protection device. Number 3 refers to the 3-phase conductors, Chris, the 3-phase conductors that's coming to this 3-phase panel. Number 3. Number 4 refers to the neutral conductor that comes with this panel. Can you guys see that? Number 4 refers to the neutral conductor. Number 5 refers to the grounding electrode conductor that goes to the ground rod if this is a service entrance panel. Only you need number 5 if it's a service entrance panel. Okay? And number 6 refers to the system, to the building, what do they call it? Main bonding jumper or system bonding jumper between the neutral and the ground. And we only do this if it's a separately derived system or if it's a main bonding, a service panel. Number 7 refers to the conduit that need to house these 3-phase conductors and a neutral. Any question, guys, about what we're trying to achieve here? Can I have thumbs up, Chad? We understand what we're trying to achieve out of this exercise?
Difference between the service panel
the difference between a service entrance panel and any other panel is 2 things. A service entrance panel, you have this number 6, which is main bonding jumper, and you have a grounding electrode conductor going to the ground rod.
I realize that.
Yeah.
What's the difference between a service panel versus another type of panel?
From how they look identical. They look identical, they act identical, the only difference is they provide some type of a means where you can bond the neutral to the ground. And the overcurrent protection device have to be bolted to the panel.
So would this be the first panel?
This would be the first panel.
Okay. And everything else besides?
Everything else underneath it will be sized exactly the same. The only difference is you don't have 5 and 6. Okay? Any question, guys, about this? Okay, so let's go ahead and size all these stuff. The first thing we need to do, guys, is size the overcurrent protection device. I have them done for you. So I'm going to, when we size panel, Dustin, we always size panels based on amps. We don't size panels based on kVA. There's no, you can't go, I want to buy a lighting panel, 15 kVA lighting panel. This is not how we size it. We size it based on amps. So that's why I need to go calculate the amps for this system. I have 150 press divided by 1.73 because we're dealing with three-phase, and the voltage is 480. And that will give me 180 amps, right? This is give me 180 amps. Cool? Any question about this? I got 180 amps. Now, you have two options. Go custom design yourself 180 amps, or go to the standard industry, typical industry standards, and buy yourself a panel. So, what? So then you take 180 amps and take them to where? This is where I want you guys to take them. We're going to take them to DeWalt 3-12. Can you guys go there? Under panels.
35 amps when I multiply 150,000 or divide 150,000 by.
I was getting 180.
Review your calculation then, Chris. Two rules. So if you guys go under panel boards, DeWalt 3-12. Can you guys go there? DeWalt 312, panel boards 312. Okay, can you guys see on the top of that page, it has the standard industry three-phase? Three-phase, so I have 180. What's my next standard from 180? Can you guys see that? My next standard is 200. Everybody can see that? My next standard is 200. So my next standard amp panel that I'm going to go install in my building is 200. Any question? Any question about this? Everybody knows how to size the panel. Number one is actual copper inside the panel. The copper inside the panel. Okay? The overcurrent protection device is piece of cake. We also size it based on 180. You take the 180 amps. Take 180 amps. This time, guys, we have the NEC code book 240.6. Go all the way to NEC 2011. NEC 2011. 240. If you guys go there, the next standard overcurrent protection device is what? Surprise, 200. So we have a match. We have a match between our panel and our overcurrent protection device. Typically, William is not here. Typically, Rob, my friend, the overcurrent protection device must be equal to the panel or smaller. Can't be bigger. The overcurrent protection device must be equal or smaller to the panel. So if you have a 400 amp panel, I can put a 200 amp circuit breaker in it, or protecting it, or 300, or 350, or 400, but I can't put the 500 amp circuit breaker to protect the 400 amp panel. Can I get you guys to understand? The panel size must be equal to the overcurrent protection device or less. Yes, sir.
You know, we have 175, and what the current listing that we are having is 180.
Go up.
I understand.
Yeah.
What is the implication if you go down? Because I think this one is very important.
Oh, very good point. Why can't I go down? I have 175. Should I go to should I go to 200? Or very good point. I can go down to 175, so I'm down by 5 amps, or up to 200, and I'm up by 20 amps. By 20 amps. This is really, as an engineer, you can go either way because your name is going to be on it. Cover your butt type design is follow the code. If I, as a Chad Curdy registered engineer, came up and I said, you know what, my judgment said 175, and I won't install this piece of equipment, guys, and it doesn't work, it's overloaded or something happened to it, give it to Gary Ryman. Gary reviewed the calculation, the code says if it's not enough, here's your load, Chad, you undersized it. So, your judgment as a designer. rule of thumb, safer. You're going to see me going down, guys. In some application, I go down. In a smaller, here's my rule of thumb. In a smaller panels, it doesn't bother me to go up like 200 amp in this case. But when we reach the 1200 amp and 1600 amp panels, you start to be very cautious about going up a lot. But on a up to 400 amps going up is not a big deal. You start going higher than 400 amps, 600 amps, you start to really, technically you have to go up. In the test, I want you to go up. Safer, you go up. Am I clear about this point? Engineering judgment, you have to use your judgment.
You're going down, your reliability is nuisance, not safe.
Your liability is safety too. You have a load that's more technically a load that's bigger than the sublime. So if you, but what could happen? What could happen is, yeah, if I want to pull 180 amps from 175, would I burn the panel? No. Why? Because it's a 175 will trip. So yeah, you can argue it's really not. You're not going to burn the panel as long as you break it at 175. But you could exceed the. But yeah, so it's not completely safety issue. It's not going to burn the panel. It will be inconvenient for you to change the trip. Yeah, nuisance too. Absolutely. No problem. Any question, guys, about this? So this is my panel. Yes, sir. Can my breaker be smaller than panel? Absolutely. I can have, absolutely. I have a panel 200. I can put a 15 amp circuit breaker to protect it. That's kind of ridiculous. Or a 50 amp, or 100 amp, or 150 amp, or 175 amps, all the way up to 200 amp. So if I might have to write this one, guys, I want to say panel size must be, how am I going to say that? More or equal to overcurrent protection device size. Oh, not size, Chad. Overcurrent protection device size. Let me grab this one, move it away here. So overcurrent protection device size. Makes sense? So your panel have to be equal to the overcurrent protection device or more. Meaning the overcurrent protection device have to be equal to the panel or less.
And is that also called panel rating?
This, yeah, panel size is panel rating, absolutely. Any question, guys, about this? Good point, good discussion. Did you guys get your milk today or what? Everybody's jumping in, and did you get a lot of good breakfast this morning? Okay, any question, guys, about this? This, I can't emphasize this rule is very important, guys, right in here. Okay, so let's go to number 1 and 2. So we size 1 and 2. Ungrounded conductors, the 3 phases, phase A, phase B, and phase C. The ungrounded conductor, guys, when I size them, if you guys remember, the amps was 180 amps, right? And the overcurrent protection device was 200 amps. Now, take this. Code-wise, I can size the conductor based on 180 amps. Code-wise. Good design, match the overcurrent protection device. So I'm going to write here, match overcurrent protection device. So I'm going to go match my overcurrent protection device. So I have 200, and I always put disclaimers next to each. CSK, this is my initials. Everything I put CSK next to that is Chad Curdy's opinion. When you go work in the industry, they tell you dumber than rock, you take it out the window and do what your supervisor wants you to do, right? So this is match overcurrent protection device, that's an opinion. Safer opinion. I think it's safer. Match. Okay, now you take your 200 amp, and first, where do we go? We're going to go to 310.15 B16. She got married. Change your name under 75-degree column Celsius. And I need how many conductors? I need 3 conductors, guys. Why 3 conductors? Because I have 3 phase. And if you go there, Each one of these conductors have to be 3-aught. What type of insulation, Chad? I'm using THHN unless I know otherwise. I'm using THHN, assuming it's a dry location. I could use THHW too. Okay, the reason why I put the insulation because I need to size the conduit later, so I want to put the insulation.
Just a whole question, Chad. It doesn't say THHN 75-degree column.
THHN is rated for 90 degree. If it's rated for 90 degree, then you can use it. Then it's good for lower. Yeah. Okay, I have a vehicle can run at, I can drive it, it goes all the way up to 120 miles. Can I drive it at 80 miles? Yeah, does that make sense? It's the limit on that vehicle. Speedometer cannot go higher than 180 miles, say. Can I drive it for 80 miles? Yeah, no problem, this is good. Okay, any question guys about the ungrounding conductors? Ungrounding conductors? Ungrounding conductors, the phases. Cool, everybody got that one? Okay, let's go to the grounded conductor. The grounded conductor, guys. Okay, here's my rule that keeps changing. Definitely, Chris, for a grounded conductor, if your panel is 225 amp or less, CSK is my initials, full neutral. If your panel, again, opinion, if your panel is 225 amp or less, full neutral. Otherwise, if your panel is more than 225 amp, the first 200, leave him alone. Anything over 200, cut them by 70%. And if you don't believe me, this is from NEC 2011 220.61b. So everybody understand that slide? Everybody understand this slide? We've used it before. The only thing I want to emphasize, the green stuff is an opinion. Can you guys write everything you see CSK is an opinion? So if it's less than 200 here, anyway, you can't cut it anyway. So look at that, 225 or less, just full neutral, don't even mess with it. Okay? Now the code says you size it based on unbalance. We're engineers and designers, guys. We go a little bit step higher than the code. Okay, so with this, what do you say, grounding conductor. So in a case like this, so everybody knows what my size is going to be then. I'm going to use, what color? I'm going to use blue. Then my size is going to be 1 conductor because let's just say my overcurrent protection device was what? 200, right? So I'm going to apply this rule on it. Since it's 200, which would be the panel size based on the code. In a case like this, I have 1 conductor, number 3-aught, A, W, and G, and T, H, H, N. THHN. THHN. Yeah, absolutely. It's just match. If it's if the panel, a full neutral means match the ungrounded conductor. Everybody knows what a full neutral is? A full neutral means you match the ungrounded conductor. Okay, should I write it here? Full neutral means match ungrounded conductors. Okay? So that's what a full neutral means. Match ungrounded conductor. Ungrounded conductor. Any question about this? That's a piece of cake, huh? So I have 4 conductor, 3-aught each. 4 conductor, 3-aught each. Okay, number 4. Any question about number 4? That's a neutral. If you don't have a neutral, then you don't have to do this calculation. But we have a lighting panel. We're burning. That's typical like you guys doing in a project. We're burning. Our lighting panel is 200 amp. That's exactly what you guys are going to be for your panel. 200 amp panel. Okay. The second thing, grounding electrode conductor. That's the one that we go to the Mother Earth. If, can you guys write an F here? Grounding electrode conductor, if service panel. If service entrance panel. Only we use this. Only we use it if it's a service entrance panel. Can you guys put this disclaimer? This is only if it's service entrance panel that we use it. Okay? This one, guys, you go to 250.66. So you're going to take, based on the largest overcomputation device, AWG. You're going to take this one to table 250.66. We are in the copper unless I tell you otherwise. And that will get you a healthy one conductor. Number 4. What insulation? Number conductor number 4 could be bare, covered, or insulated. Any type. So I'm going to say bare. Bare, covered, or insulated. Can I guess you right? So this could be, doesn't have to be insulated. Could be bare, covered, or insulated. Typically, a lot of engineering project guys are insulated. They have an insulated conductor, it looks nicer, protected, and so forth. But really doesn't need to be insulated. The one right underneath it, guys, main bonding jumper. Main bonding jumper 250.28D is the code article that goes to it. And it will, you go to the same table, 3-aught AWG, go to the same table. It refers you to the same table, table 250.66. And when you go there, you're going to end up with number 1 conductor, number 4, bare, covered, or insulated. Bare, covered, or insulated. Bare, covered, or insulated. Most likely it will be covered or insulated in a panel. That's the one that you tie the neutral to the ground. That's the one that you tie the neutral. They call it grounding the neutral. That's the one that we ground the neutral with. It's called main bonding jumper. In this case, actually, it's, yes, main bonding jumper. Main bonding jumper. That's what the code, 250.28D. And that will get you the main bonding jumper, guys. If these conductor crits are more than 1100 kcm, we have a different calculation later on we're going to be using. Any question, guys? Now, Phil, we have just sized your lighting panel in your project. That's your guys. That's what you're going to be doing. The lighting panel in our project, Chris, do you agree with me that it does not have a service conductor? Can I also get you guys a main bonding jumper? This is only, can you write here, if service, oops, I'm going to actually refer the note that I wrote up here. So this apply to this, and also, oops, and this apply to this. Can you guys write yourself a note right here? It says, if service entrance panel, then you do these two. Otherwise, Tau, you don't have to do it. If it's a lighting, like a new lighting panel, doesn't exist. There is no main bonding jumper in the lighting panel, and there is no grounding grounding electrode conductor. Any question, guys, about this? So hopefully these step by step, taking it easy. A couple of examples will walk you through all the sizes that we're going to be doing before we send you to the industry. The last thing we need to do, there is no good designer without a conduit. If you don't know how to size a conduit, you're doomed. Electricians know how to size a conduit. You guys should be at least one step above electricians. Oops, did I say that? So I'm going to go size my conduits. For conduit size, guys, that's piece of cake. I'm going to take, I have 4 conductors. Remember, I have 4 conductors. Each one of them is 3-aught A, W, and G, right? And if you go to NEC 2011, chapter number 9, and which table? In this case, we don't need to even, because they're all the same, we go directly to Annex C, right? Annex C. Annex C directly. If you guys go, because they're all the same size. And oh, by the way, what type of conduit, Chad, do you want? Up to this point, have I told you guys what type of conduit do I want? PVC schedule, did I write it down? Yeah,
Yes.
right here, PVC schedule 80, done, you should look, Chad. And what do I need? 2.5 inches, 2.5 inches. So I have 2.5 inches, 2.5 inches. 2.5 inches. The conductors are, we should write the conductors insulation too, Chad. THHN. Guess it defeats the purpose if you're using PVC, most likely it will be THHW, but we are pulling it in a dry location, THHN. Any question guys about using NXC? You guys want to go?
If you calculate it,
It will be
you
different.
could get 2 NXCs over by a half inch. And then NX is not supposed.
You go to chapter 9. Chapter 9, NXC is
Conventional only.
yeah, but you are allowed to use NXC though.
And you could use a 20.
2.5. Yeah. It'll be interesting to see how. Yeah.
This can you show us how you get 2.5?
2.5. Oh, I'll show you right here. Let's go directly into the NEC code book. Annex. Let's go directly to Annex. What did we say, gentlemen?
You said NXC.
Did I say Annex C? Annex C.
785.
785. Thank you. 785. Let's go directly to the page. How about that? Cool. 785. So let's. This is metric designator continued. Maximum number of conductors. That's not it. 785. Well, it's different than mine. Okay, we're gonna go into Annex C. C what? Which C is that? C. Which C? C.
C9.
C9. C8.5. Thank you. C9. Here's C9. C9. Maximum number of conductors in rigid PVC conduit schedule 80. I have THHN. I'm going to go all the way to THHN. THHN. Here's my THHN. Can you guys see where the THHN is here? Everybody can see that. And how many conductors do I have? Let me see if I can grab my highlighter here. Okay, highlighter. So here's my THHN. I need 4 of them. So that will be, right? 4
That's 2 inch.
all the way. It gives you 2 inch. Oops. So why did I go for 2.5? Was I drunk? 4 conductors,
Future.
2 inches. No, you guys are cool. 2 inch. So you are right, Chris. I hate to admit it, but you are right, buddy. Somebody has to be horsewhipped, huh? Okay, so let's go back, and you're absolutely right. It should give you. Thank you. That's good. It should give you. Oops. There you go. Oops. Where am I here? Oh shit. I don't want transparent. Okay, so I'm gonna go erase this baby and give me 2 inches. Thank you. Oops. Grab this, Chad, and grab this. What did we say, guys? 2 inches? 2 inches. 2 inches. Love it. 2 inches. Any question, guys, about this? So no conflict. Yes, sir.
What's the difference between maximum number of conductors and maximum number of compact conductors?
Compact conductors are a special type of conductors. Most conductors, guys, come in circular stranded conductors. They look like this. Okay, these are the conductors. Cool. This is conductor. Compact conductor, a specially designed conductor that they make the stranded different. And I'm gonna. Can you guys see that? Almost. And I'm exaggerating here. Can you see there is no, each one of these is a strand, so there is no space between the stranded. That's why they call them compact.
Using all the space.
Yeah, they get rid of all the space. So if this is 4/0, if this is a 3/0, and this is a 3/0, this will be, the diameter will be smaller, so you can fit more of these in the same conduit. That's the compact.
So it's not a cable, it's a conductor.
It's a conduct. Well, it's a cable is misleading. A cable could be a single conductor cable, or a multi-conductor cable. It is a conductor. So, does that make sense? So they make them in a way where they compact the copper or aluminum of these strands, so they can fit more of them in one conduit. Where would you use it? Only retrofit. You would never, 99% of the time, you're going to be non-compact. Only the compact if you get into a situation where you don't want to tear down the conduits and you want to upgrade your system. A good application is to use compact conductors. Good point. Aluminum or copper. No, they're not solid. They're stranded conductors. All these are strands.
So they're probably thinner.
They just design them. They compact them. They design them differently. They're not round, so they design them differently. They use it for retrofit, so you don't tear down your conduit system. So you have a 3-inch conduit, and you want to move from, say, 1/0 to 4/0. So, but if you are to move to 4/0, you're going to get a bigger conduit. Then you use compact conductors. They can fit in a smaller conduit size. Good point. Any question, guys? Or did you get your milk this morning, or what's going on here?
Didn't we just use compact in the first place?
No, not for new design. Yes.
It's big, making circular wiring is used to dies, make it smaller and smaller. If you haven't, make it trapezoidal and triangular or square shapes.
It takes, absolutely. So why wouldn't we use this one and start with? Very good point, Nick. The price, expensive. Okay, any question, guys? Good. That's it. So we size a lighting panel for you guys. Your lighting panel is sized. Let's jump into, do you guys want to break, or shall I jump directly into the second one? Second one is the same thing, same calculation, except it's a mechanical panel now. Mechanical panel, the same calculation, and I really want to emphasize these guys, same calculation. But here's what I want you guys to know. I have a mechanical panel. So, Chris, 100 kVA. Where the heck did you come up with the 100 kVA, Chad? Can I guys get you to look me in the eye? 1,000. Can I get you to look me in the eye and say, Chad, we know how we got the 1,000 kVA. Here's how we got it. We took the largest, fattest, fluffiest motor. We multiplied it by 1.25, multiplied by the voltage, multiplied by the 1.73. Here's the kVA for the largest motor. Then we added the kVA for all the other motors, lump sum them all, and we came up with 1 kVA demand. Everybody knows where the 100 kVA is, because mechanical equipments are not rated in kVA, most of them. They're rated in horsepower. So what we do is, if it's a 15 horsepower motor, you take the amps from the code, multiply it by 1.73 because 3-phase, multiply by the voltage, which is nominal voltage we use, 480, add them all up, and you end up with a demand of 100 kVA. You guys have done this for me when we did the calculation for the mechanical panel. Any question, guys, about the kVA? I can't emphasize where the heck did you throw up this number, Chad? That's from what you guys calculated, or what we calculated. Okay, so we have it's a mechanical panel, meaning just feeding mechanical equipment. I need to size the same 7 things. Any question? The same voltage, by the way. And everything we talked about from now on is 3-phase. No single phase, no baby. Single phase is for Mr. Ryman and his babies. Oops, I'm recording here. Only for the babies, a single phase. You go into guys, in a design, single phase, you grab the panel, single phase throughout the window. It's not worth putting single phase in a building that has a 3-phase. Okay, any question, guys, about what we need to do? So you guys have the graphic right in front of you. Let's go hit it. This is where I want you to pay attention to what you have just done. So let's go directly into example number 2. Example number 2, Chad. Okay, the first thing I want to do for this one, let's use blue. Blue is good. I'm going to take the 1000K, Chris, divided by 1.73 times 480. That's how we find the amps. And I came up with 1204 amps. Okay? 1204 amps. We're going to use the same rule that Chad gave you. The rule is 1204. I want you guys, please, to go to DeWalt under 3-13 this time, because you can't, not 12. 13 will give you the switchboards because we ran out of the panel boards. We're going to go to switchboards now. And what's the next standard? What's the next standard? 204. What's the next? 1204. What's the next standard? Look at the three-phase, not the single phase, the three-phase.
Well, let's just go to the,
Hold your horses. The next standard, I'm going to write it down here first. The next standard is 1600 M. What's the one below the next standard? 1200 M. Huh? Hold your horse. Now that's where the judgment becomes. If you go to the wall, guys, your next standard panel is 1600 amp. Now, would you jump 400 amps to get 4 amps? Can you guys see the difference? If I want to go up, I'm jumping 400 amps to get me a 1600 amp panel. For what? For getting 4 amps. Now, that's where you use your engineering judgment and you say, you know what, Chad? I'm going to go lower. And again, CSK. So in this case, guys, my options are either to go up to 600 or down to 400, and the only difference is how much? 4 amps. That's the only difference, 4 amps. In this case, I feel very comfortable for 4 amps to go to jail, and 1200 amp would be good. Okay? That's the judge.
10% cutoff.
Okay, now, thank you. Now, what I wrote here, again, CSK, meaning if nobody agrees with it, throw out the window, no hard feelings. If you are 10% above a panel, you can, that's my cutoff, my personal cutoff. So if I'm 10, especially if I go in a higher amps, and again, this is really my personal cutoff, 10%, so meaning if I have 1200 amp, if I have 10% on the 1200 amps, I feel comfortable going down to 1200 amps. Higher than 12%, I like to go up. Do you see what the 12% cutoff here? That's related to, so let's do this one. What's 12% plus 1200? What's 12% 1200?
Are you at 10% or 12%?
I'm sorry, 10%. What's 10% of 1200?
120.
120. 120 plus 1200 is what? Do it.
23. Thereabouts.
100,
That's okay.
13, 23, 23, 20, 13, 20. Up to 13, 20, I feel comfortable going down. My cutoff. Higher than 13, 20, I like to go up. Now, can I go for 13, 20 up? Yeah, you can, no problem. Again, this is really engineering judgment that you have to make. Okay, so right next to it, CSK. In this case, definitely, this is, I wouldn't hesitate going down. I would not hesitate going down. Now, some of you might say, Chad, have you accounted for future expansion? Remember, you should have accounted for future expansion here, another 10%. So all these, you feel more comfortable. Now, when they came up with the 1,000, that including continuous, non-continuous, and accommodated for future expansion and so forth. Okay. Any question about the 1200 and why we came up with 1200? Makes sense, Nick? No? Okay. This is easy decision because it's just 4 amps. Okay, so we move down into the next, my friends. You're going to go to. So we got my 1200 amp. I need my overcome protection device. I have 1204, the same thing that we did. We're going to take it to 240.6 and EC 2011. If you go there, now, am I going to go up or down here? What's up? Let's do that again. Up 1600 amp. Down is what? 1200. But guess what, Alaribo? I already made up my mind going down by the panel. Can I go up even here? If I made the panel 1200, can I go to 1600? It's not an option. So because I made up my mind to make the panel 1200, the circuit breaker must be 1200 or less. I have no other option. Does that make sense, guys? Okay, so now you're going to start to think like a designer. ungrounded conductor match over connection device. That's piece of cake. I have 1200 amp. I'm going to match it. I need to run 4 runs. I can't carry 1200 amp with one conductor unless you use bus duct. If you do that one, you have 300 amp. Take it to 310.15B16 under 75-degree column press. And how many conductors you're going to get? You guys proved me wrong already. So I'm going to have how many sets? I have 4 sets. Why 4? I decided Chad Curdy single-handedly to parallel 4. You could have parallel 3. 4 and 3 conductors. Each one of these conductors is what? 350 kcm, and the insulation is THHN. Any question, guys, about this? If I parallel 3, what would I get? 3 runs, 400 amp, that would give me 600 kcm. Big conductor. That's why I went to 4. Because I want to stay around, hover around 400, 500 kcm. 400 amp, 500 kcm. Any question, guys, about this? Okay. Ungrounded conductors. Make sense now? No? Okay. So let's go to the grounded conductor, the neutral. The neutral. The grounded conductor, guys, for my grounded conductor, I will start with the 1200 amp. Remember, because that's how we size the ungrounded conductor. That was the reference for sizing the ungrounded conductor. Then, is this more than 225? Like we just saw that rule, 225 amp? Yeah, definitely more. That's where I apply the rules of this rule, which we're gonna see. What is it? So I'm gonna go. So I take the first. Let's take this here. This first 1200 amp. The first 200 amp. What do you do with them? Leave them alone. 220.61B. I believe this is where we got this. So we're going to do it in neutral. 220.61B. The first 200 amp, don't mess with them, Chad. If you take 200 amp from 1200, what do you left? 1000. What do you do with this? Cut it by 0.7, add them up. Okay? Everybody knows what I'm doing here? So we've done it multiple times, not the first time. So you end up with 900. That's what Alaribo is telling us. So my neutral have to be 900. I want you to understand, Alaribo, that I already made up my mind to parallel how many sets? 4. I have no choice now. I'm stuck with 4. So I have, I take the 900 amp then. I have to parallel 4 this time because I already made up my mind. So that'll give me 225 amp, and you're going to go to 310.15B16 under 75-degree column. And when you go there, you're going to end up with 4 sets, because I ran 4, of 1 conductor. Each of them is 4-aught, and A, W, and a G, and a T, H, H, N, and done. Can I get you guys to understand if the phases are parallel 3, then I have to parallel here 3. And Alaribo and Chris, can I get you guys to understand if this number is less than 1-aught, you have to make it 1-aught, because you can't parallel more than 1-aught for power. Less than 1-aught. Did I say more? Sorry. Less than 1-aught for power. Almost there. Any question, guys? Nick, does it make sense?
I just missed you on that last one.
You can't parallel conductors less than 1-aught by code.
Oh, okay. Yeah.
Yep. So if that number was less than 1-aught, like it was number 2, I came up with number 2 here, I have to up it to 1-aught. Okay, let's go to number 5. Grounding electrode conductor. We're going to do the same thing for grounding electrode conductor. Grounding electrode conductor, here's the rule, guys. You take the number of sets, multiply it by ungrounded ungrounded conductor, conductor size. So please write yourself the rule. When you pedal, you have to take the number of sets multiplied by ungrounded conductor. So how many sets do I have, Olaribo? 4. What was the size of the ungrounded conductor? Not the neutral, the ungrounded conductor. 350 kcnm. What would that give you? It will give me 14. Oops. It will give me 1400 kcnm. Okay. Now 1400 kcm is more than 1100 kcm, right? So what I need to do, this is the check that you have to do. If it's more, then you have to apply this rule. I'm sorry, no, this is for the, this rule is for the, we'll do this one and we're doing the ground electric conductor. You guys are awake, I am sleeping. 14 kcm, take it directly to 250.66 under table, and that will get you the largest, fattest, fluffiest conductor you can get is what? And it has to be bare, insulated, or covered. I like to put the minimum is bare, but it could be fully insulated, covered, or bare. 3/0. Can we go higher than 3/0? That's the largest that we can get. Any question guys about the rule? If you go to under table 250.66, that rule is right under the table. All right, number 5 and then number 7, and then we're done. Give you a break. Cool? Can I move? No? Okay. Main bonding jumper. Main bonding jumper, the same thing, guys. For the main bonding jumper, we're going to take the 4, multiply it by the 350, exactly the same thing, kcm, 1400 kcm. 1400 kcm is more than 1100 kcm, right? We'll check here. So these are the rules that we're going to do. The last thing then, you're going to take the 1100 kcm, multiply it by this magic number, which is 12.5%.
Don't you have to multiply the 1400 by 12.5?
Thank you. You have to multiply the 1400, because that's what they were dealing with. The 1400, you have to multiply by 12.5%. Right? Everybody knows how to multiply by 12.5%, which is 0.125. And if you do this math, this will make 400k multiplied by 0.125. That will get you a healthy 175 kcnm. Okay, up to this point, I have no clue what size conductor is this. Do you? Anybody knows what size conductor is this? There is no 175k. So you need to identify it. 175 kcm. I need to re-identify that baby from chapter number 9, table number 8. If you go to chapter 9, table 8, find a conductor that can give you 175 or larger. What's the conductor that can give you 175 kcm or larger from table 8? That will give you one conductor, number 4 hot. Thank you. AWG, bare, insulated, or covered. Bare, insulated, or covered. Bare, insulated, or covered. Everybody knows what the 4 came from, Alaribo? The number of sets.
No, why how did you get that number 4 hot?
Because if you go, you need to find 175 kcm. So go under the kcm column and find 175 or larger. And cross-referencing it with the number. Yes, sir?
On that, I was just reading it. It says, not less than 12% of the area of the largest phase conductor.
Yep.
Would that be one phase instead of all 4?
No, one phase if you're not parallel. If you read right underneath the table 250.66. under table 250-66. It tells you if you're paralleling, you have to do the multiply by the 6. Did you find it, Alarigo?
He's showing.
Sure, okay. All right, the last thing, guys, is piece of cake while you were thinking of this, the conduit size. I decided to use rigid, Chris, just to bother you. We're using rigid. For rigid, I have 3 conductors number 350 kcm THHN. If you take this one to chapter 9, why did I switch myself? I will start right here. I have 3 conductors number 3. Oops, this is not a nice 5. 350 kcm THHN. Take this one to chapter 9. I'm sizing the conduit, guys. It's a rigid. And chapter 9, table 5, number 5. That will get you 3. You multiply by the cross-sectional area of 0.5242. 0.5242. Correct me, Chris, if I'm wrong here. And 1 conductor, the neutral, was 4 aught A, W, and G. Same thing, T, H, H, N. Same table. Chapter 9, table number 5. And if you, this will give you 1 conductor multiplied by 0.3237. 237. Add them up. You can add them up. Okay? And that will get you a healthy 1.8963. This is a square inch. And then up to this point, we have no idea what this is. 1.893 square inch. Take this baby into rigid metal conduit. Table number 4. And 40% fell because they have, 4 more?
Yeah.
And then that will give you more than 2. 4 sets. I have 4 sets of how many conductors? 2.5 inch rigid metal conduit. Rigid metal conduit. Did they do a mistake here? No? Comes up with 2.5. Thank you. We have another gentleman to verify. 2.5 inch rigid. Any question, guys, about this? Straightforward. Let's take 5 minutes break and we'll continue. Camel meat. Okay. Last example. So I'm going to bombard you guys. We did a lighting panel. We did the mechanical panel, similar to the mechanical panels that you guys had on the lighting panel. Now, guess what we're doing? We're doing a receptacle panel. We're doing a receptacle panel. I switched for the receptacle panel a few things here, Chris. I have a load. What happened to my load? Oh, here, right here. I have a load. I have 210 kVA load. Now, how did I come up with this load? 210 kVA load. I took 180 volt amp times the receptacles in my building, then derate them, everything higher than 10K. The first 10K, leave them alone. Anything higher than 10K, cut them by half. Remember, guys, how we did the receptacle calculation? And I demanded this load, and I came up with this lump sum fat, fluffy 210 kVA load. Can I get you guys to understand that 210 kVA is a demanded load? Okay, Rob, can you give me a thumbs up? I understand that this kVA is a demanded load. 45 degrees working good too. Okay, everybody understand 210 is a demanded load. Okay, since it's a receptacle panel and since we are in Minnesota, the voltage that we use for receptacles is 120. And 208 is the line-to-line voltage, right? We burn our receptacles in the US at 120. If we're burning them at 220, all what you have to do is going to be 380, 220. Okay, so here's what we need to do. Number 1, the panel size. Number 2, the overconduction device for the panel. Number 3, the 3-phase conductor. Number 4, this time, the neutral conductor. Number 5, Chris, I changed 5 for you. Number 5 this time is the equipment grounding conductor. This is not a service panel. Can you guys see? There is no 5 and 6 that we're grounding electrode conductor and main bonding jumper. They don't exist because this panel is not a service entrance panel. It's not a service entrance panel, and we're not doing the bonding inside the panel too. And number 4 and 5, okay. Where's number 6? Am I jumping in 4, 5? Number 7, I have is the number 7 is the conduit size.
6 is not required.
6 is we dropped it out of the numbers here. We dropped 6 out of numbers. I think to match what we did in the past, isn't that what we did? So we got, okay, so let's go ahead. I don't have number 6, so don't sweat it too hard. Oops, main bonding jumper. Let's go.
Number 6 was main bonding jumper, and we don't have it.
Yeah, number 6. What was number 5 too? Number 5 was the grounding electrode conductor. Number 5 was the grounding electrode conductor. So, okay, let's just continue with this. When say number 6, you know what? Okay, so let's just continue with what we have. There is no number 6. Any question, guys, about this? Okay, let's go size. The first thing we need to size our my friend. We need to size, where are we here, Chad? We need to size the amps. So we have 210K divided by 1.73 times the 208 system that we have. That will give me 583 amps. 583 amps. Now, Chris, you and I know to size the panel, we need to go to some type of an industry reference that DeWalt give you close enough to this, and instead of going to these Cutler Hammer catalogs and Square D guys. I like what DeWalt have summarized them. We can go to 2-12 this time, and that will give me a 600 amp, right? 600 amp. Now, can I have a disclaimer here? Can I have a disclaimer? May I have a disclaimer? Say yes, Chad, we have a disclaimer.
Yes,
Probably only a fool will put a 600 amp receptacle panel. So what would I do then? I would split them into 2, but we're not going to do that. Usually, guys, if you have receptacle panels, you're going to stick with 225 amp to 300 amp panels. If you have larger than this, throw another panel, and a third panel, and a fourth panel. So, but we don't care. We have a concentration of load in one area, and we have a 600 amp load. Okay, so we got the 600 amp. Let's go to the overcompression device, Chris. We'll do the same thing. 583 amps. Take it to NEC 2011 under 240.6 non-adjustable circuit breakers. Give me 600 amp. Just molded case, non-adjustable circuit breakers. Piece of cake, right? That's not a big deal. A lot of you are making me hungry now with that smell. Any question, guys, about 1 and 2? Piece of cake, we've done it many times. Okay, let's go to ungrounding conductor. Ungrounding conductor, for my ungrounding conductor, again, CSK is my initials, so that's match overcompression device. You don't have to match overcompression device. You can size it based on the amps as long as the overcompression device is the next standard. Engineering wise, match overcompression device. So match overcompression device. So I have 600 amp. I think, Chris, is a good idea to parallel here, right? Anything higher than 400, always parallel. Good idea. So that'll give me 300 amps. And if you take this one to table 310.15 B16 under 75-degree column, as we have done many times, that will give me the following. That will give me 3 conductors because it's 3-phase, and the conductor size is number 350 kcm, and the insulation I'm using here THHN, and don't forget that there are 2 sets of. So this is a 2 sets of. So how many total conductors do I have? 6 of them, right? But it's always writing, guys, 2 sets of. Don't never write 6 conductors. Very misleading. Can I get you guys? Never ever write here 6 conductor number 350 kcm. Very misleading. It's when you say two sets of, three stands for the three phases. Now we understand three phases. Three phases, each one of them is 350. That's how we write it. Two sets of, three conductors, 350 each. Any question, guys, about this? Chris, did you come up with the same number? Okay, your calculators are agreeing with us. That's good. All right, the grounded conductor. Remember Mr. Curry's rule, 220.61b, that we derate. Good idea to derate. If you have 600, I know it's a receptacle panel, but if you have a 600 amp receptacle panel, most likely you have other loads with it. I hate to call it receptacle panel and derate, but 600 amp. I'm gonna apply my rule of the first 200 amp. Don't you ever mess with them. These are sacred cows and goats. Take the 600 amp minus 200 and cut it by 0.7. And oh, by the way, don't forget to add them up. So that will give you a 480 amps.
So we're just doing this pure exercise, but we would go full.
On a receptacle panel, yes. I wouldn't size a receptacle panel more than 300 amp. I wouldn't install any receptacle. Actually, 225 is the largest. Like if you would, when you do size the receptacle panels, add all the loads. If you end up with a panel that more than 225 amp panel, what do we do? Just split them into two panels. Like Chris in our project, it would be one 225 amp panel in the first floor and another 225 amp panel in the second floor. Okay. Okay, so I need to parallel because I have no other option. Divide by 2, that will give me 240. Same thing, 310.15 B16 under table, 75-degree column, and you see that will get you how many sets? That will give me 2 sets of one conductor. You have to say not just one 250. How many? One conductor. 250 kcm THHN number, and that is my size. Any question, guys, about this? Any question about this? I kind of spelled these a little bit, 600 minus 200 to emphasize that. So I have a 250 kcm. And the 350, do I have, what was the size again? For the 250 kcm and 350 for the phases. That's not bad. Can I go back to my diagram, guys? And just adjust a few things. Did we use 7 for, what did we use 5 for? Did we use 5 for, no, not before, grounding electrode conductor. So what I'm going to do, guys, I'm going to just make dotted lines here where it's not needed. And I'm going to say here, that was number 5, wasn't it? Before that was number 5, and there was here that was number 6. These are not needed, and I'm just going to name this one for conventional. I want to call this number 8. Okay, number 8, just to continue. So can I get you, and I'm going to write 5 and 6 not required. Then guys get you to continue with the same kind of convention that we did. 5, which is that one, the number 5 here, dotted line here. 5 and 6 are not required for this because it's not a service interest. Can you guys, if you write yourself a note, 5 and 6 are not required because, and change this one to 8. I'm going to call it 8. Just convention. To stay in the same convention that we've done. Okay, so let's go back to number, the ungrounded conductor. We got that one, the grounded conductor. Let's go to number, now I want to say a number, this one is going to be, in this case, number Can you guys change this one to number 5? And I'm going to say 5, and I'm going to change these one to 5 and 6 are not required. And I jump directly into item number 8, as a matter of fact. Item number 8. Just naming things. Okay, everybody's on the same page? Item number 8 now, called Equipment Grounding Conductor, EGC. You guys have seen that many times. Many times, right? Okay, the changes that I did in red for what you guys have. So what I'm going to do, I'm going to write now the equipment grounding conductor. Everybody knows what the equipment grounding conductor is supposed to ground the equipment. That's the ground. Yes, sir.
8 before 7.
Why is it before 7? But just because I'm too lazy, I don't want to erase it and put 7 before. That's all. I made a mistake, basically. Do you want me to put it? Yeah. Just these are number convention, guys. They don't mean anything other than just getting you some type of a form of. And another thing, you have to size the equipment grounding conductor in order to size the conduit, guys. Otherwise, you can't size the conduit. Okay. So, Chris, we're going to we size it based on overcurrent protection device. So, overcurrent protection device equals 600 amp. So, what I do is I take the 600 amp. So, this is the first thing you need to do. You're going to take the 600 amp to where? Table 250.122. And what do you guys get?
Number 1.
Okay, so we take the equipment grounding conductor. We take number 1. So that will give me number 1. Most likely is going to be T, H, H, N. Oops.
But you had with parallel.
Thank you. So that's what we're going to do in a second here. I'm going to use 2 sets. Oops. I need 2 sets of one conductor number 1, A, W, G, T, H, H, and N. I hate when I ran out of rule. T, H, H, and N. T, H, H, N. Okay, so I'm going to highlight this one with some type of a color here. Here you go. Okay, why 2 sets? Because the code guys say if you have an equipment grounding conductor and you parallel, you have to pull the same size equipment grounding conductor with every set of parallel conductors.
Can
The
that
same
be
size.
less than 1 aught?
Can this be less than 1 aught? Yes. This one can be less than 1 aught.
Because it's not current.
It's not current carry conductor. You're absolutely right. This one, guys, very good point. This one, and you know why also, Chris? Because I'm not paralleling it. I'm not paralleling 2 ones.
Oh, you're doing full.
I'm doing full in each one of them. Each one of them has a full. I'm not paralleling, really. In reality, I'm doubling it. Right? I'm not paralleling it. Okay, so this is number 1 in each conduit. 5 and 6 not required because it's not service. Conduit size. Let's go size the conduit, Chris. Chris is going to do that conduit sizing for us. So let's take 3. The first thing I'm going to start right here. 3 conductors number. Don't have a whole lot of room here. 350 KCM THHN. You're going to take it to the same table. This is chapter number 9, table number 5, as we have done in the past, and this will give me 3 conductors number 0.5242, 0.5242, and then I have 1 conductor in each set, 250, number 250 KCM THHN. That's for the neutral, right? Same calculation. 1 times 0.3970, 0.3970, I think, or is it 6? 70. Thank you. And the last one, what do you think the last one is for? What? The ground. So this is a number 1, A, W, and G, T, H, H, N, all the way. This baby is 1 times 0.1562. 0.1562. Add them up, and that will get you a healthy. Did I put the second table here? So a healthy 2.126. 2.126 and 4, just to be different than press, square inch. And this is the size that we came up. Everybody knows what we're doing, guys. And I'm going to just put I'm going to put an indicator here. These are for phase. This is neutral, and this is ground, right? Everybody knows. It's like crap here. When you go to the parameters. So this one is, oops, all right, you guys write it. I want to have, this is MChat, ground, this is my neutral, this is my phase. This is my phase. Everybody knows that? Neutral, ground, and phases. Okay? So let's go size the conduit. When you guys are done typing this. And that's it. That will be sizing our conduit. I came up with 2 point. Oh, by the way, did we say what type of conduit do we need? Did we emphasize? Yeah, it's an EMT. We're using EMT. Now, why should we pull an equivalent conductor with EMT? For reliability, better grounding, you can justify it to your boss. But do I need to pull an equivalent grounding conductor with EMT? No. But we're pulling it anyway. A good word to justify it is longer distances. The longer distances, guys, the more EMT become less reliable in terms of a high impedance. They become high impedance, they don't trip the circuit breakers. That's approved. So
the question is, if this is a panel, how far is it from the service center?
Let's say it's 400 feet. If it's 400 feet, probably I have to have a voltage drop issue there. I might have to size based on voltage drop. All right, so the last thing I'm going to do, guys, is I want to take my, right in here, my 2.126 square inch. Take this one to table number 4. Chapter number 9, and it's a E, M, and T, and this is a 40% press. All this will get you how many conduits? 2 conduits. Why 2? 2.5 inches EMT. Done. Why 2 conduits? Because we're paralleling too. We're paralleling. We are paralleling. Any question, guys? Any question? Before I let you guys break for lunch here, homework number 5. Homework number 5. Owner equipment panel, P1, based on example number 3. You're going to go this one based on example number 3 in the sheet. The load is 1354 kVA, 1354 kVA. The voltage, Chris, says we jumped all the way to our Canadian friends and to New York, and we burned these equipment to 600. Any problem with that? We're burning the equipment to 600 line to line or 347 line to neutral. It's used very few places in the US. They use 600 volt.
Owner, what is that scratching mean?
Owner equipment.
No, word owner.
Here?
Yeah.
This is P-1, panel 1.
Oh, okay.
Just I gave it a name.
Okay.
Okay, let me read it one more time because my handwriting is a chicken scratch. Owner equipment panel, P1, based on example number 3. Everybody knows what example number 3 is in the book, in the assignment. The load, this is the demand load, already demanded for you, 1,354 kVA. The voltage system is 600 line to line, 347 line to neutral. So tell my friend, when you do all your calculation for the amps, which voltage are you going to be using? The higher voltage, right? The higher voltage. Any question, guys, about this? I hope these 3 examples and the homework will get you guys any panel you should be able to size it. Lighting panel, mechanical panel, receptacle panels. Later on, Chris, everybody got that one and you guys have a copy of it? Later on, let me tell you what we're going to be doing, something I haven't done yet. Can you guys see this receptacle panel? Now, here in the US, we burn the receptacles at 120, right? So we need a transformer ahead of it. I do have a couple of examples later on, not now, not today, that will match a transformer to a receptacle and size the cables between the transformer and the receptacles and the cables that's going to feed the transformer. Right? So I have not done an example where I match a transformer to a panel. You guys are going to be doing a transformer to a panel. Yesterday, a lot of you asked me what size transformer do I need, and what did I tell you to do? I say take the amps of your panel, multiply by the voltage to it, multiply by 1.73, go to DeWalt, and find yourself a transformer that can get you this kVA or higher. That's what we're going to be doing. But I do have 3 examples, really good ones, that goes through the whole calculation. Match a transformer to a panel.
Isn't it about the reverse of that other transformer calculation?
Yes. Yes. Except on the other transformer, we didn't do, did we do the primary? Yeah, we did the primary.
Well, we started with a supply and came
Yep,
up with
yep. The only difference, Chris, on the transformer calculation is we didn't worry about what's going to be set on the secondary side. There's a little tweak. If I have a transformer that's going to be feeding a panel, what I end up doing, I end up matching the full load amp of the transformer to the full load amp of the panel, and they're mismatched. So that mismatch is the only thing I want to do. I can get you my 2 cents of how to do the mismatch. Because you find a transformer that gets you 83 amps, and there is no 83 amp panel. So I want to go to a 100 amp panel and size everything for 100 amp. So it's not really rocket science. Yep. Any comments, guys? Any questions about this? Comments, questions? Board size.